Welcome to Module 1, Introduction to Data Structures and Algorithms. In this module, we'll explore the foundations of how data is stored, organized, and processed efficiently using structures and algorithms. Slide 2 Agenda. Here's what we'll cover in this session. First, we'll understand some basic terminology. Then we'll look at how data structures are classified, followed by key operations on data structures. We'll also explore the concept of abstract data types, and finally, we'll discuss algorithms and their characteristics.
Let's begin with the basics. Data is any elementary value, or a collection of values, like a student's name or ID. Group items refer to data made up of sub-items. For example, a name might include first and last names. An entity represents a class of objects and is defined by its attributes, such as a student's name, age, and marks. Basic terminology, Part 2. A field is a single piece of information, like age or name. A record is a combination of multiple fields, such as a student's full profile. A file is a collection of similar records, for example, the data of all employees in a company. In programming, a variable is a memory location that stores data. Data types define the kind of data a variable can hold. For example, integers, floating points, characters, and strings are all data types that tell the compiler how to interpret the stored data. Types of data types. There are two types of data types: system-defined or primitive data types like int, float, and char, and user-defined data types such as structures in C or classes in Java. These allow us to group different kinds of data together for more flexible and meaningful data handling. Need for data structures. Data structures help us organize data, store and retrieve it efficiently, manage large datasets, and perform operations like searching and sorting quickly. This makes our programs scalable and efficient.
Data structures. Data structure is a particular way of storing and organizing data in a computer so that it can be used efficiently. A data structure is a special format for organizing and storing data. General data structure types include arrays, files, linked lists, stacks, queues, trees, graphs, and so on. Classification of data structures. Data structures can be classified into linear and nonlinear types. Linear structures like arrays and stacks access elements sequentially, while nonlinear structures like trees and graphs store and access data in a hierarchical or connected fashion. System-defined data types. Primitive data types. Data types that are defined by system are called primitive data types. The primitive data types provided by many programming languages are int, float, char, double, bool, etc. The number of bits allocated for each primitive data type depends on the programming languages, the compiler, and the operating system. For the same primitive data type, different languages may use different sizes.
System-defined data types, also called primitive data types, are predefined by the programming language. Depending on the size of these data types, the range of values they can store also changes. For example, an int may take either 2 bytes or 4 bytes of memory. If it takes 2 bytes, or 16 bits, it can represent values from -32,768 to +32,767. This is written as -2 to the power 15 to 2 to the power 15 minus 1. If the int type takes 4 bytes, or 32 bits, it can store values ranging from -2,147,483,648 to +2,147,483,647. This is written as -2 to the power 31 to 2 to the power 31 minus 1. The same concept applies to other primitive data types as well. User-defined data types. When the system-defined data types are not sufficient, most programming languages provide the ability to define custom data types, known as user-defined data types. Examples of these include structures in C or C++, and classes in Java. In the code snippet shown on the left, we are combining multiple system-defined data types, like integers, floats, and characters, into a single user-defined data type called new type. This approach offers greater flexibility and ease when managing memory in computer programs. Most popular data structures: array, An array is a collection of data items stored at contiguous memory locations. The main idea is to store multiple items of the same type together. This structure makes it easier to calculate the position of each element by simply adding an offset to a base address, that is, the memory location of the first element of the array, usually represented by the array's name. As shown in the figure, an array initialized with values 2, 4, 8, 12, and 16 occupies consecutive memory blocks, and each element can be accessed using its index. A linked list, like an array, is a linear data structure. However, unlike arrays, the elements of a linked list are not stored in contiguous memory locations. Instead, each element, known as a node, contains the data and a pointer to the next node in the sequence. This allows the linked list to dynamically grow or shrink during program execution. As shown in the diagram, each node points to the next, forming a chain, and the last node points to null, indicating the end of the list.
A stack is a linear data structure that follows a specific order for performing operations. This order is either LIFO last in first out or FILO first in last out. In a stack, all insertions and deletions are done at only one end, called the top of the stack. As shown in the diagram, the push operation adds an element to the top, while the pop operation removes the element from the top. This structure is commonly used in function calls, undo mechanisms, and expression evaluation. Stacks support several common operations. The push operation adds a new element to the top of the stack. The pop operation removes the top element from the stack and returns it. The top operation, also known as peek, returns the last inserted element without removing it. The size operation gives the total number of elements currently in the stack. And finally, the isEmpty operation checks whether the stack is empty or not. These operations form the core functionality of any stack-based implementation. A queue is a linear data structure that, like a stack, follows a specific order for performing operations. However, the order in a queue is first in, first out, or FIFO. This means the element that is inserted first is also removed first. In a queue, elements are added at one end and removed from the other. A common example is a queue of consumers waiting for a resource, where the one who arrived first gets served first. The key difference between stacks and queues lies in removal. In a stack, the most recently added item is removed first, whereas in a queue, the least recently added item is removed first. This diagram illustrates how a queue works. New elements are added at the rear, also known as the back or tail, through the enqueue operation. In this example, the number 9 is being enqueued at the rear. On the other end, elements are removed from the front, also called the head, using the dequeue operation. Here, the number 2 is being dequeued. The queue maintains the first in, first out principle, where the earliest added element is the first to be removed. Data structures are broadly categorized into two types, static and dynamic. A static data structure has a fixed size, meaning the amount of memory required is determined before the program runs. Arrays are a common example of static structures. On the other hand, a dynamic data structure can grow or shrink during execution, adjusting memory usage as needed. Linked lists are a typical example of dynamic structures. Understanding this distinction is key to choosing the right structure for a given problem. A static data structure has a fixed size, meaning the memory allocated to it remains constant throughout the program's execution. While the contents of the structure can be updated or modified, the overall memory allocation cannot be changed. An example of a static data structure is an array, where the size is defined at the time of declaration and remains the same during its lifetime. Dynamic data structure. A dynamic data structure does not have a fixed size. Its size can be modified during the execution of the program, based on the operations performed. These structures are designed to allow flexibility in memory usage by adjusting their size at runtime. This makes them ideal for situations where the amount of data isn't known in advance. An example of a dynamic data structure is the linked list, where memory is allocated and deallocated as elements are added or removed. Static data structures have a fixed memory size, meaning their size is defined at compile time and cannot be changed during execution. In contrast, dynamic data structures allow their size to be updated during runtime, which can be more efficient in terms of memory usage and adaptability. Static structures generally offer faster access to elements because of their predictable memory layout. However, dynamic structures provide greater flexibility, allowing the program to allocate and deallocate memory as needed. Various operations can be performed on data structures, starting with traversing. Traversing means accessing each data item exactly once, allowing it to be processed, for example, printing the names of all the students in a class. Another key operation is searching, which is used to find the location of one or more data items that meet a specific condition. For instance, identifying all students who scored 100 marks in mathematics. It's important to note that the searched item may or may not exist in the data structure. Operations on data structures. Continued inserting is used to add new data items to an existing list. For example, adding the details of a student who has just joined the course. Deleting refers to removing a specific data item, such as the name of a student who has left the course, from the collection. Sorting is the process of arranging data items in a particular order, either ascending or descending, depending on the requirement. For instance, arranging student names alphabetically or ranking participants based on their scores. Lastly, merging involves combining two sorted lists into a single, sorted list, which is useful when consolidating data from different sources.